Hi everyone, my name is Brooke Butler, and for our Chapter 7 discussion, I will be talking about our general chemistry review over Lewis structures, formal charge, resonance, bonding, and hybridization. Lewis structures. Lewis structures are diagrams that show bonding between atoms of a molecule and the lone pairs of electrons that may exist in the molecule. To find the Lewis structures, we have to be able to count valence electrons. Valence electrons are the outermost shell of electrons that are associated with an atom. So, to count valence electrons, go to your periodic table. For our first example, we'll be using carbon. So, to count valence electrons, it's quite simple. So you're just going to count over, going left to right, over to carbon. So, carbon's on the right, and we're going to start left. So carbon's on the right, and we're going to count left. So you're going to count 1, 2, 3, 4. Our answer is 4. This is the number of valence electrons found. So if we count how many we could go over in total, we could go 1, 2, 3, 4, 5, 6, 7, 8. This is how many we want in our orbital. We want 8, so then we can have our compound as happy as it can be, basically. So, since we only have 4 of the 8, it wants to bond 4 times. So, bromine. We're going to do the same thing. But when you are counting over, you can see bromine goes through all of these elements. Transition metals do not count when you're counting valence electrons. So we're going to count the exact same way. 1, 2, 3, 4, 5, 6, 7. So it has 7 valence electrons. And so 8 minus 7 means it only wants to bond 1 time. Again, with bonding, there are ionic and covalent bonds. Ionic bonds are metal and non-metal bonding. Metal and non-metal bonding. When covalent is 2 non-metals bonding. Sorry, I couldn't spit it out. So, with this bonding, you'll have cations and anions. Cations are positive and anions are negative. The positive means it does not have as many electrons as it would like, and it is not electrons are negative, so it's going to have a positive charge, but anions have this excess of electrons, so it is making it more negative. Examples of this are NH plus and Cl minus. A way to show your valence electrons is through a Lewis dot symbol. So right here, if we look at sulfur, we're going to count over to the sulfur right there, finding the valence electrons. 1, 2, 3, 4, 5, 6. So we have 6, as we can see right there for sulfur. So we're going to place that 1, 2, 3, 4, 5, 6, trying to make it look equal and nice because it helps with bonding later and explains with our formal charge. So, to calculate formal charge, we need to know the number of valence electrons subtracting minus the number of non-bonding electrons, and then the number of bonds in a participating atom. Sounds like gibberish, but I'll explain. So, example, ammonia. Ammonia is NH3. So I have it drawn here. We have our N, which is at the bonding site, basically. And then the H is connected with 2 lone pairs. So, first we need to find the number of valence electrons. We have 2 ways we can do this. First, we can count over to nitrogen. There should be 1, 2, 3, 4, 5, as written here. Or you can just count. So you have the 2 lone pairs, so 1, 2, and then each one that it connects. So 1, 2, 3, 4, 5. Again, same number. So, to continue on, we need to subtract the number of non-bonding electrons. This would be our lone pairs. And as we can see, we have 2 dots indicating our 2 lone pairs. which is why we have the 2 there. And then finally, we subtract the bonds in the participating atoms. So these are where it actually connects, and these are the actual just the things that are bonded to. So this would be our hydrogens, and we have 1, 2, 3. So 5 minus 2 minus 3 equals 0. So that means there is no formal charge and there's no ions, positive or negative. For our next example, we have NH4+. The plus kind of gives away that there is going to be a cation, but we will continue on. Again, we have this nitrogen, and then 4 hydrogens connected and our plus. Again, let's find our number of valence electrons for nitrogen. We can count over 1, 2, 3, 4, 5, which we did there, or 1, 2, 3, 4, and the plus is included, making 5. And then, how many non-bonding electrons do we have? Well, I do not see any lone pairs, so it's going to be 0. And then, the number of bonds in a participating atom, I got 4, because we just have to count what is connected. We have 4 hydrogens connected, but the plus does not count, because it's just saying that we are missing an electron, and it's not actually connected. So it's going to create a +1 cation for the formal charge, meaning it is less stable than the ammonia we have here. Resonance. Resonance is the movement of pi bonds and lone pairs of electrons. Gibberish, right? Well, basically, it's just how something can be written and shown in different ways. And it shows the movement of it. So we see CO3, 2- here, and there are 3 different ways to show it. Technically, they're basically all the same, but it just has that movement of the pi bond in all the different places. There are 6 rules for estimating stability of resonance structures. So, rule 1, the greater the number of covalent bonds, the greater the stability, since more atoms will have complete octets. Again, covalent bonds are 2 nonmetals connected, as we have here. Number 2, the structure with the least number of formal charges is the most stable. None of these are that way, they're all the same. So, 3, the structure with the least separation of formal charge is the most stable. 4, the structure with a negative charge on the electronegative atom is more stable. 5, positive charges on the least electronegative atom, most electropositive, is more stable. And 6, this is the one that applies here, resonance forms that are equivalent have no difference in stability and contribute equally. So, these all have the same formal charge of -2, but they're just in separate places, but that doesn't make them nonetheless different. Bonding strength. Oh, length and strength, sorry. But bonding length and strength. Usually, the shorter the bond, the stronger the bond, and then vice versa, the longer the bond, the weaker it is. So an example here is we have carbon sigma bonded, which means there's only one connector with another carbon, versus carbon pi bonded to another carbon, which means there's 2, or a sigma bond on top and then a double bond on that. So the single bond is considered larger or longer. Therefore, carbon double bonded to carbon is stronger. And again, when you think about it, the double bond is making it more stable. It can't move as much as the sigma bond is. And the more stable it is, the stronger it will be. Next, going on with length and strength, we have elements play a large part too. If an elemental bond is small, it is strong because of its closeness. So in this next example, we'll have to see which one is smaller. So carbon sigma bonded to chlorine versus carbon sigma bonded to bromine. So the chlorine is a smaller element than bromine. Therefore, the carbon chlorine is stronger. As you can see here, when we pull up the periodic table, the bromine has a mass of almost 80 and the chlorine is about 35.5. Therefore, the chlorine is definitely smaller. And since it is smaller, it can just keep everything closer and more stable to keep it stronger so it can't just go breaking off into new bonds and everything. Hybridization. Hybridization is the mixing of atomic orbitals into new hybrid orbitals. This happens because you want to exchange the energy for bonding purposes. With hybridization, you have s and p orbitals. What are s and p orbitals? Well, on page 5.5 I have here, an s orbital has a sphere of electron density and is lower in energy than the other orbitals of the same shell. And you can see the nucleus is here. But then a p orbital has a dumbbell shape, as we can see here, and contains a node with no electron density and at the nucleus, which is in the same place. It is higher in energy than an s orbital. So this means that we are always going to want to fill our s orbital first, because lower energy is the same thing as saying it is more stable. And the reason that we're going through this hybridization process is to make a bond that is more stable. Everything is just trying to become more stable. So, sorry, I got a beep on my phone. But we will use this example here with carbon. So, with carbon, we are going to want to fill using valence electrons. Again, looking here, we see 1, 2, 3, 4 valence electrons. So we're going to want to fill our orbitals here. Remember, 2s is what we always want to fill because it is the most stable. And the way we fill is with up and down arrows. But you can see here, this counts as 1 and this counts as 2. We still have 2 more to go. So we need to fill the 2p, but we always have to fill up first. So it will look like this and this to fill the 4 of the carbon. Say it was nitrogen, or not nitrogen, it was oxygen. Then we'd fill up again and then go down. That's just the order in which we do it because that's what will make it most stable in the hybridization process. So when we hybridize it, there is an energy change. So what we are wanting to do is we're wanting to fill all of these spaces because that will complete the orbital, and that is what we always want. So this here will go up to fill everything. So we'll have 1 up, 2 up, 3 up, 4 up. And so we only have the 2s filled there once, but filling the 2p actually makes it more stable because we have our carbon connected in all 4 places, as you can see here with the sigma bonds making the tetrahedral shape. This is also known as sp3, but it's just written differently to explain the fundamentals. I will show you on the next page. Here, sorry, that was my example page, but we are going to talk about sp3, sp2, and sp orbitals. So, to explain sp3, we're going to use methane with this, which is CH4. So, we are going to draw our carbon because it was the main connector within the compound. So, we're going to do the same thing as we did before. 1, 2, 3, 4 valence electrons. Fill it up the same. We're going to sp3 hybridize it, but this time we're going to specify the sp3, and we're going to fill it across like we did before. This means there are 4 unpaired electrons, and it's going to make this tetrahedral shape. The s and p orbitals combine together to reduce the steric hindrances, and is usually in this tetrahedral shape. There are only sigma bonds. These things here are just showing that it's going backwards and forwards, and 4 single bonds, single bonds and the lone or 4 lone pairs, but see, we have it all connected there. Then we're going to sp2 hybridize. We cannot use this again because you cannot double bond H's, and that is what happens in sp2 hybridizing. So again, we're going to use carbon as our middle connector, so we're going to write it the same. And then we're going to hybridize it over and create a whole new setup. So one of our P's goes up, as you can see in sp3, it will go up and separate itself so it can make that double bond. So again, we're going to fill it like we did before, and the s and p orbitals combine. The other p orbital is either a pi bond or contains a non-pairing pair of electrons. Usually it's just going to be that double bond though. 2 single bonds, like you see here, and 1 double bond, and it is usually trigonal planar, as I've drawn here. Finally, we have sp. Again, we're going to use that carbon shape, and we're going to hybridize it over, but we're going to lift another p up so we can create another double bond. Just adding another layer on top. So the sp orbitals combine, as you see here, and the other 2 orbitals for pi bonds form 2. 1 single bond, as we see here, and 1 triple bond. And this will usually be linear. If it's not, I would be slightly worried, but it's going to look like this. I also took the liberty of creating each one. This is sp3, again, tetrahedral shape. Then we have our trigonal planar. Again, you see this is not a hydrogen. Hydrogens cannot double bond. And then we have our sp hybridized, this triple bond right here, and I just had the liberty of doing it carbon triple bonded to another carbon, and I put the hydrogens on the outside just so everything was connected. Thank you guys for listening to my discussion for Module 7. I'm excited to see the other videos. Thank you.